Today is November 15th, 2011. We're going to review Chapter 4. First question we're going to take up is from page 232, 4D. They are asking us for the amount of intercepts. There's a couple ways we could do this. We could turn this into standard form and then use the discriminant. But an easy way to do this would be actually graph this function. Since it's in vertex form right now, this is our A, our H, and our K, which we have over there. We're going to plot the vertex. So remember, our vertex from vertex form is essentially the opposite of H and the value of K. So the vertex of this will be positive 5 and positive 2. So we go over 5 up 2. My A value is negative 3, which means my parabola is going to be facing downwards. So because it's facing downwards, let's see if this will work. There we go. We're going to have a parabola that's going to cross the x-axis twice. So the question asks, how many x-intercepts does this have? This will have 2 x-intercepts. Okay, so the exact same question, say we couldn't remember how to graph this. So I wanted to use what we learned before, which was the discriminant in this lesson. The discriminant is b squared minus 4ac. Now remember, we're in vertex form. So this essentially is y is equal to x minus h squared plus k. A, H, and K. Our discriminant is using b squared minus 4ac. I'm just going to color them for you. This is our B, our A, and our C. One hint to this, that you can't actually put these specific variables into the discriminant, is that they're not the same letters. We actually don't have a value of a C and a B in vertex form. We're using what's called H and K. So right there, that should give you a hint that I can't actually plug those numbers directly into the discriminant. I need to change the equation. I need to change the equation into standard form. Standard form is where we can take the variables and put them into the discriminant. So when we're in standard form, we'll be able to use this discriminant. So I'm going to actually change this question into standard form. And in order to do that, I'll have to expand and simplify. So we're going to expand. And in order to expand, remember I have this base, x minus 5 squared. So we're going to be using our FOIL or rainbow method to expand this. X minus 5 times x minus 5 plus 2. So first I'm going to deal with the brackets. Negative 3 will stay on the outside. X times x will give us x squared. X times negative 5 will give us negative 5x. Negative 5 times x, negative 5x. And negative 5 times negative 5 is positive 25 plus 2. Now along with that, I'm going to have to simplify my like terms. And I'm going to have to distribute the 3 into every term inside. So first, I'll collect my like terms. So we'll have x squared minus 10x plus 25. Then when we go to distribute the 3, we'll multiply each of the terms by 3. Or sorry, negative 3. So negative 3 times x squared is negative 3x squared. Negative 3 times negative 10x is positive 30x. Negative 3 times positive 25 is negative 75. And on the outside of the brackets, we have plus 2. When we finally collect our like terms at the end, which are 2 constants, in standard form, this equation reads negative 3x squared plus 30x minus 73. Now I have an A value, which is negative 3, a B value, which is positive 30, and a C value, which is negative 73. I now plug that into our discriminant. Change our view here. So now with the discriminant, our B will be 30 squared. Subtract 4 times A is negative 3 and C is negative 73. 30 squared is going to be 900. Negative 4 times negative 3 is going to give us positive 12. Positive 12 times negative 73 is going to give us negative 876. And when we subtract those, we're going to get 24. So, because this discriminant is greater than 0, how many x-intercepts do I have? 2. Which is exactly what we found in the previous question when we did that. Just to prove it, we're going to plug the formula into our graphing calculator and make sure we've done this correctly. Okay, so we have our formula here. This is in vertex form. We go to plug it in. Now I'm going to have to zoom out clearly, or at least move the graph over. When we move the graph over, we found that our vertex is at positive 5 and positive 2, and because A was negative 3, it was opening downwards this parabola, which makes perfect sense. What I'm going to do is I'm going to put our standard form equation in and show you how the computer graphs it as the exact same thing. So we're going to add another equation. The standard form of our equation was negative 3x squared plus 30x minus 73. So plus 30x minus 73. We're going to equate this one. And if you notice, it drew a line directly over the other one. So the calculator reads them both as the exact same. Whether we're in vertex or in standard form, we still have the exact same parabola. Question number 6 on page 240. Okay, question 6. It says the population of a town is modeled by this function. P at t is equal to 6t squared plus 110t plus 4,000. P at t is the population, and t is time in years after year 2000. Okay? So, 6a asks us for the population in the year 2020. So, since our function has the variable of t is equal to the year 2000. So, we're trying to find the amount of years after t. In the year 2000, t is actually the value of 0. So if in year 2000 t is equal to 0, what will t be in 2020? So, in other words, to find the value of t in the year 2020, we have to actually take our new year, 2020, and subtract it from the base year, which is the year 2000. That's going to give us a value of 20. Once we have that value of 20, we're going to plug it into our equation. So our equation will read P at 20 is equal to 6 times 20 squared plus 110 times 20 plus 4,000. 20 squared is 400. 20 times 110, 2,200, that makes sense. 2,200 plus 4,000. 6 times 400 is 2,400 plus 2,200 plus 4,000. The population in the year 2020 should read 8,600 people in the town. That's a small town, relatively easy question. Question B asks us, in what year will the population be 6,000? So in other words, they want to know when will P at T equal 6,000. Into P at T. So we're solving for T. What year? Our function again is P at T is equal to 6T squared plus 110T plus 4,000. Now this question's a little more difficult. I need to plug 6,000 in for P at T because that's our final population. The problem is I have two terms as variables. I have T squared and I have T to the power of 1. There are 3 different ways to solve this question. We can either factor it, find our 2 values of T. We can put it into the quadratic formula, or we can put it into vertex form. All 3 of them will allow us to isolate T. In order for those to work, we have to make sure the equation is equal to 0. So I'm going to move 6,000 over to the other side of the equation. This will be 0 is equal to 6T squared plus 110T minus 2,000. I move 6,000 over, it becomes negative. We have negative 2,000. So I'm going to solve this 3 different ways for you guys. We're going to try by factoring the start. It may be a bit difficult, but we're going to give it a try. So we'll take this equation. I can. I can do all 3. Okay, so one of the first ways I could have done this is I can factor this. So I'm going to take the factors of 6, 1T and 6T, 2T and 3T. Our factors of 2,000, it's pretty obvious that 2001 isn't going to be a pairing. Either will 2 and 1,000. We're going to go with numbers that will be a little closer together. For instance, even 20 times 100, maybe 50 times 40. I'm only writing out 2 of them because I'm trying to find the fastest way to factor this. Let's quickly do some trial and error to see if we can solve this question. They'll give us 40 and 300. That won't work. 60 and 200. No. 80 and 150. That's going to give us a difference of 70. It's not enough. 120 and 10. That's no good either. So, after looking at this, clearly if I write out all these factors, it's going to take me a very long time. So instead of doing that, we're going to move right into quadratic formula. We're going to put our quadratic formula, which I'm going to put Okay, so we got our formulas back. Quadratic formula gives us the value of x. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So in our equation, our a is the number 6, our b is 110, and our c is negative 2,000. We need to plug these values in. So we're going to get negative 110 plus or minus the square root of 110 squared minus 4 times 6 times negative 2,000 divided by 2 times 6. So we're going to quickly equate these numbers. This becomes negative 110 plus or minus square root 110 squared, 12,100. And we have negative 4 times 6 times negative 2,000. Positive 48,000. We're going to get 2 roots for sure, divided by 12. Negative 110 plus or minus 48,000 plus 12,100. 60,100. So we're looking for the square root of that number. Divided by 12. We're going to square root that term, 245.2. So we get negative 110 plus or minus 245. We'll round it to 0.2 divided by 12. This is where we have to split the equation. We have, because we square rooted a number that was positive, we have a positive and negative value as our answer. So we're going to get x is equal to negative 110 plus 245.2 divided by 12. And we're going to get x is equal to negative 110 minus 245.2 divided by 12. Oh, thanks, Sam. So we get 110 negative plus 245.2 divided by 12, 11.2. Or our other option is 110 negative, subtract 245.2 divided by 12. Negative 29.6. So we have to make sense of these two.
The positive one. So which one do you take? The positive one and the negative?
We're going to figure that out right now. So since we're starting at the year 2000 and we're going into the future, we have a growing population. We're going to be using the positive value as our answer. So since that's our positive value and they want to know what year it is, they're going to be looking for us to add that value to 2000. So we have 2000 plus 11.2. So in the year 2012, and 0.2 would be how much of a, maybe 2 months, 3 months down, I think it's 3 months. 11. And 3 months. But essentially in the year 2011, population will equal 6,000 people. Okay, we could have also solved this question. Say you couldn't remember the quadratic formula. If we complete the square and put this into vertex form, we can isolate because we'll only have one variable. So I take 6 and I divide it by the first two terms because I want t to be by itself. Our common factor is 6 times t squared plus 110t divided by 6 minus 2,000. We got to take our b value, divide it by 2 and square it, which is going to be 110 divided by 6 times 2 squared. 110 over 12. And we're going to end up with 110 divided 12 squared, 84. So I quickly did this, and the number we're going to add and subtract is 84. I rounded it. It should be 84.00, but, or sorry, 03. We're going to leave it as 84. What's important is our square root's going to be this number, 10 divided by 12. That's essentially what we're going to have in the brackets at the end when we go to square it. So we'll leave it as a fraction, as 110 squared. When you divide by 2 again, when you divide a fraction by another number, it's the same as just multiplying the bottom numbers. Divided by 144. So we're actually going to use this fraction instead. So we're going to add and subtract this fraction. That way it's a little more accurate.
Good afternoon.
Alright, don't worry about it. Alright, so we were going to use 84, but it won't be as accurate. Technically, the number we're going to square root is going to be this one. So I squared this fraction, and I got this fraction. I squared 110, got 12,100. When I squared 12, I got 144. So that's the number we're going to add and subtract. We have to take out the negative term. So when we take it out, we have to multiply by our 6, right? So we have 6t squared plus 110t divided by 6 plus 12,100 divided by 44.
He says this point's good for entering certain body cavities.
Okay. We got to multiply this fraction. So I'll take the top term, which is 12,100, multiply it by 6. I can probably reduce this fraction. We'll work on it after. But we're going to get negative 72,600 divided by 144 minus 2,000. Does this make sense so far? Eventually, when we go to collect our like terms, because I have the number 2,000 and I have a fraction over 144. But right now, I just want to actually get to where I am. So the next part is I'm going to square root the first and last term. I know what the square root of the last term is going to be. It's going to be the fraction I worked with earlier. So we get 6t. Because that's positive, it's a positive sign. And when we square root it, we're going to get 110 over 12. Does that make sense? It's 110 over 12. The reason I know that is because it's the exact number I'd used earlier, right? When I squared. That part's going to be squared. Let's actually just turn this fraction into a whole number. So it's 72,600 divided by 144. 504.1, we'll say, okay?
Please make sure your attendance sheet has been sent down. Thank you.
That's me. So now that we have this, remember when we started this whole equation, it was equal to 0, right? So we go back down. Technically, this is 0 is equal to 6t plus 110 divided by 12 squared. I collect my two like terms on the outside. So this is negative that number minus 2,000. So we're going to get negative 2,504.1, which is rounded as that. Now I got to isolate for t. So what I'm going to do is I'm going to move this to the other side of the equation. When I move it, it'll become positive. So we'll get 2,504.1 is equal to 6t plus 110 over 12. I can turn that into a decimal 2. We'll just go one step at a time. Next, I'm going to move that 6. So I have to divide both sides by the number 6. On this side, we'll be left with t plus 110 over 12 squared. On the other side, we have that number, positive this time, divided by 6, 417.3, we'll say. 417.3. The next step is I got to get rid of that square root, or that squared term. So I square root both sides of this. Essentially all I'm trying to do now is isolate t. When I square root both sides, I'm going to get t, sorry I won't need brackets, but t plus 110 over 12. Square root of 417 is 20.4. Let's fix that equal sign. I'm going to turn that fraction into a decimal so we have an actual term. So 110 divide 12, 9.1 let's say. So I've done quite a bit of rounding, so the number will probably be a little different. And finally, I move 9.1 to the other side of the equation. We'll get 20.4, subtract 9.1, 11.3. If you remember, our other answer was 11.2. So because of our rounding, we're up by about a tenth towards the quadratic formula, but this is just another method you could use to solve it. All right. So this was our formula. I'm going to quickly graph it. Probably have to zoom out to get all of it. Here we go. So I get the feeling it goes extremely high into the air. But what's important when we zoom in is we take a look at our intercepts. And our intercepts, that's probably our 11.2. And whatever our other negative, I think it was like 29 was our other intercept. So those were the two numbers we were looking for.